We were talking about moment generating function, and any moment generating function is indicated by mx of t. It is a function of t, and it is given or defined as expectation of e power tx, and hence for a given PMF or PDF p of x, the moment generating function will be total of e power tx into x for all values of x, or integration of e power tx into f of x with respect to dx. We were also looking into some of the properties. Just give me a minute. Okay, so what we do, how this generate moment is, we will differentiate this generating function with respect to t, and you put t is equal to 0. Now in some cases e power t is defined as s, so e power tx becomes s power x. So the moment generating function thus becomes expected value of s power x. And what you have to do now, this will be a function of x, s rather than t. Instead of putting t equals 0 after differentiating, now we'll be putting s is equal to 1 in order to simplify the moments. Now in the same case, if you put s is equal to 0, this is somewhat also called as the probability generating function. So we'll looking into the properties of MGF. So we look into three properties. The first property is that MGF is unique for a distribution, and if you want to obtain the MGF for any uh, random variable the linear form where p is absent. So max of t is given by mx of ta. Right? If you know the mgf, just replace t by ta. That will give you the mgf of ax. And we talk about mgf of sum of independent random variables. Mgm of sum of independent random variables. Then we said summation of I equals 1 to n xi t is given by product of I equals 1 to n m xi of t. So multiply all the mgf's to get the joint mgf of the random variable sum. And for two cases, we could say m of x plus yt is equal to mx of t into my of t, provided x and y are independent. Otherwise, you have to use the definition. What is definition? Mx plus yt. So if x and y are not independent, then mxy of t is nothing but expectation of e power t x plus y, and for a bivariate case, that will be double summation e power t x plus y into p of x comma y. So using this, you can obtain the MGF whenever the variables are not independent. Now the combination of 2 and 3 can be taken as the fourth property, where you're talking about the linear uh, combination of the variable, where you take say y is equal to ax plus b, and then myt will be equal to m of ax plus bt, and that will be given by e power bt into mx of at. That will true now. And if you take similarly the linear combination of the sum of independent variables, like say max plus by, where x and y are independent, a and b are constants, then this will be mx of at plus my of bt. So let us see how to prove this. So we'll be using the definition. So consider myt by definition, that is expectation of e power ty, but y is nothing but ax plus b. So this will be summation. So as said, I'll be proving for the discrete case. You have to do the same thing for the continuous case into the probability function p of x. So when you simplify this, you will get e power atx into e power bt, which is a constant, so it can be taken outside the summation sign. So it will be left with e power bt into summation of x belonging to x, e power atx into p of x is equal to x. So which can be written as expectation of e power atx, which is nothing but the mgf of x with at. So your e of mgf of y, where y is equal to a plus bx, is e power bt into mgf of x with t replaced to a. So we'll look into some examples and we'll see how well we can apply the properties and see them. So for the continuous case, replace your summation by integration sign and your p by just px or f of x. Continuous case ಅಲ್ಲಿ equal to ಬರೆಯಕ್ಕಾಗಲ್ಲ, ನೀವು notation px use ಮಾಡಬಹುದು in place of f of x, but don't write p of x is equal to x. X is equal to x is probability mass function. If you just write px or fx, then that could serve as both PMF as well as PDF. Okay, so ಇಲ್ಲಿ t ಒಳಗಡೆ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ತಿದೀವಿ, ಅವಾಗ tax tb ಸಿಗುತ್ತೆ. ಅದನ್ನ ಸ್ಪ್ಲಿಟ್ ಮಾಡಿದಾಗ sum ನ it becomes product, because we know that a power x into a power y, when the bases are same, the powers get added up. So e power tax plus tb can be split into e power tax into e power bt. Now bt is an independent term of x, so that whole thing would be taken outside the summation sign. So I'll be left with just e power atx into px, which is the definition of expectation of e power atx, or the mgf of x with 8. Okay, so these are the 4 properties of.
ಕ್ಲೀನಾಗಿ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ ಸರ್.
Huh?
ಸರ್ ಕ್ಲೀನಾಗಿ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ ಸರ್, ಇದು ಬೋರ್ಡ್ ಒಂಥರ ಲೈಟ್ ಆಗಿದೆ ಸರ್.
Okay, recording ಅಲ್ಲಿ ಸರಿ ಕಾಣಬಹುದು. If not, I'll write it and send it. Okay. Okay, so let us take an example problem. So before that, let me give you PGF, which is probability generating function. It somewhat generates the cumulative probabilities, and it is defined as expectation of s power x, which is nothing but summation of x is equal to x s power x into px, or integration of s power x into f of x dx, and continuous successive differentiation of this d of expectation of s power x with respect to s, and putting s is equal to 0 will generate the probabilities. And if you put s is equal to 1, the same function serves as MGF, and it generates moments. So generally they are called as generating functions. So we take a numerical problem. Obtain MGF and generate moments. Verify. Also obtain PGF. So let me take a simple problem. X is equal to 1 by 3, or x equals 3, 6, 9, and 0 otherwise. So obtain the MGF and generate the moments, verify it, also obtain the PGF. So I'll show the verification for the first 2 moments. You do for the next 2 cases. So since it is discrete case, we go in the tabular manner. So my x values are 3, 6, and 9. And I have px values 1 by 3 each. Total comes to 3 by 3 equal to 1. Therefore, this is a PMF. If you look into the moments, so I will show the first 2 moments, x into px square into px. So Ex is equal to the first moment sigma x px, that is 18 by 3 or 6. Second central moment Ex square is equal to sigma x square px over all positive values of x, and that comes to total now 90, 100, 126 by 3, which is 42. So the first moment is 6, the second moment is 42, which is our mu2 dash. The left part of the problem is writing very detail. It should be correct. Okay. Now let us obtain MGF and see how to get 6 and 42 from MGF. Now MGF is mx of t, which is expectation of e power px, and since we are dealing with discrete distribution, it is e power tx into px. So we have to define e power tx for all the value of x and multiply that with px and obtain the total. So when I have x is equal to 3, I get e power 3t, e power 6t, e power 9t into px will give me e power 3t by 3, e power 6t by 3, e power 9t by 3. So the total comes to e power 3t plus e power 6t plus e power 9t divided by 3. So our mx of t is equal to e power 3t plus e power 6t plus e power 9t whole divided by 3. So this is the MGF. Now your homework is obtain mu3 dash, mu4 dash and check that from the MGF. Checking that from the MGF. Okay. This is clear. So rewrite the distribution if needed. Okay. Now how to generate the first moment. The first moment is defined as the first derivative of the MGF. So whatever MGF mx of t you have, you differentiate that with respect to t once and put t is equal to 0. So we have the MGF as this. When I differentiate this with respect to t, I get 3 e power 3t plus 6 e power 6t plus 9 e power 9t divided by 3. Now putting t equals 0, I get 3 into 1 plus 6 into 1 plus 9 into 1 divided by 3, which comes to 18 by 3, that is equal to 6. And that is what we have got by using the formula of the moment. So verify ಅಂತ ಕೇಳಿದ್ರೆ obtain moments and verify it from the MGF ಅಂತ ಕೇಳಿದಾಗ MGF obtain ಮಾಡಿ MGF ನ differentiate ಮಾಡಿ put t is equal to 0, that will generate the moment. Now again take the MGF and differentiate it twice successively to get the second moment. Now second moment mu2 dash is our second derivative of the MGF at t is equal to 0. So we already have the first derivative here. So ಮತ್ತೆ ಅದನ್ನೇ differentiate ಮಾಡಬೇಕು. So ಇದನ್ನೇ differentiate ಮಾಡಿದ್ರೆ I get 3 into 3 e power 3t plus 6 into 6 e power 6t plus 9 into 9 e power 9t divided by 3. So now put t is equal to 0. So taking t equals 0, so we get 3 into 3 plus 6 into 6 plus 9 into 9 divided by 3, which comes to 9 plus 36 plus 81, which is 126 by 3, same as 40. Now I'll obtain the third moment. So we could verify it from the formula mu3 dash. Our third moment will be the third derivative of the MGF at t is equal to 0. So that means you are differentiating again the second derivative. Third derivative is same as the derivative of the second derivative. So this will be, I'll get 3 cube plus 6 cube plus 9 cube divided by 3. So that should be the third moment. Now naturally, since the probabilities are same, if you use the formula expectation of x cube into p, expectation of x cube, so your x values are 369, so you are somewhat obtaining the expectation of x cube only. And if column and table al ಮಾಡಿಕೊಂಡು you will get the same answer. So this is how we generate the moments from the MGF, and this is how we identify the we compute the MGF, expectation of Tx into this. So it is a function of t being a number very now mod t close to 0 ಅಂತ ಹೇಳ್ತೀವಿ. Could be any real number ಅಂತಾನು ಹೇಳ್ತಾರೆ, depends. Okay, now obtain the fourth derivative and also compute mu3 dash mu4 dash using the formula expectation of x cube, expectation of x power 4, and verify whether you get the same answer. So this is how we compute MGF and verify the moments. Let me take another example on raw data only. So sum with respect to x. So let me say p of x is equal to x is equal to x squared by k. If x is equal to -1, 0, and 1. So obtain moments and verify from the MGF. Obtain moments and verify from MGF. So you have the values of x, values of px. So you have x values -1, 0, 1. So when you put the x value in the function x squared by k, so you get 1 by k, 0, 1 by k. So the total comes to 2 by k. Now since px is PMF, sigma px is equal to 1, which implies k is equal to 2. So this function x squared by k is now same as x squared by 2. So this will be 1 by 2, 0, 1 by 2. So the total becomes 1. So this is the PMF. Now computing the moments, so we'll have x into px, x square into px, x cube into px, x power 4 into px. The first 4 moments about origin. So I'll have -half, 0, half, x square into that will be 0, half and half, x cube will be again -half, 0, half. So the total comes to 0, 1, 0. So particular problem here, all odd moments are coming to be 0. So mu1 dash is equal to expectation of x, which is sigma x px, that is equal to 0, and mu2 dash is equal to p of x square sigma x belonging to x square px, that is coming to be 1. And if you generate x power 4 px, x power 5 px, and so on, additional columns, and if you observe the moments, you will get all the odd order moments, say mu3 dash, mu5 dash, mu7 dash, etc. All will be equal to 0, and all the even cases, all even order moments are is equal to 1. Now, if I obtain the MGF for this, MGF is mx of t given by expectation of e power tx, and in this case that is sigma x belonging to x e power tx px. So we have our px, we have x, so we'll define e power tx and e power tx into x into px. Now when I have x is equal to -1, I get e power t. When I put x is equal to 0, I get 1. When I put x is equal to 1, I get e power t. So multiplying that with the probability, I get e power t by 2, 0, e power t by 2. So the total is e power minus t plus e power t all divided by 2. So my MGF mx of t is e power minus t plus e power t divided by 2. This is the MGF. Now obtaining the first moment from the MGF. First moment mu1 dash is derivative of our mx of t at t equals 0. First derivative. So I'll have e power minus t into -1 plus e power t into 1 divided by 2. When I put t equals 0, I get -1 plus 1 divided by 2, which comes to 0 by 2 is equal to 0. Fine. Next, obtaining the second moment, mu2 dash is the second derivative of the MGF at t equals 0. Now second derivative is the derivative of the first derivative. So I'll have e power minus t into -1 plus e power t into 1 divided by 2. So when I put t equals 0, I get, so this simplifies to e power minus 0 plus e power 0 divided by 2, which comes to 1 plus 1 by 2, which is equal to 2 by 2 or 1. So you got the same answer. mu2 dash is equal to 1. Even from this, it is equal to 1. So that's how you obtain the MGF. From the MGF, you obtain the moments. So you can obtain any number of moments once you have the function MGF. But the problem is that there is no guarantee that MGF always exists, because expectation sometimes could be defined for the various ranges for x, and sometimes this quantity might be infinite. So in that case, we say MGF doesn't exist. But if it exists, it is unique. ಅಂತಂದ್ರೆ ಇದೊಂದು MGF ಇದು ಅಬ್ಸರ್ವ್ ಮಾಡ್ತಿದ್ದೀರಾ ಅಂದ್ರೆ ಈ MGF ಈ distribution ಅಲ್ಲಿ ಮಾತ್ರ ಇರುತ್ತೆ. You don't have any other distributions with the same MGF. So you can guarantee take any values of x and px as it is PMF only for your x, which is taken as say -101 with probabilities say half, 0 and half. Only for that case you will have this MGF. Now, if you are observing, say, MGF of other distribution, say you have some distribution y with, say, its MGF is also same as this, then by the uniqueness theorem or by the first property, we say that x is nothing but y. So, ಅದು y x ತರನೇ ಇದೆ, ಆದರೆ ಅದನ್ನ y ಅಂತ ಕಾಲ್ ಮಾಡಿದ್ರೆ that will also be equal to the same distribution as what we have. So this could be the distribution So 0 probability 0 irodrinda we are skipping that, not required. So if you come up with any such distribution where you have the MGF as this, that implies that if you look into the values in the probability, that will be same as what you have observed for the distribution X. So that is the meaning that MGF is unique. Now observing the second property. Okay. ಇದೆಲ್ಲ ಬರ್ಕೊಳ್ಳೋದು ಬೇಡ. ಸೊ ಜಸ್ಟ್ ನಿಮ್ಗೆ ಅರ್ಥ ಆಗ್ಲಿ ಅಂತ ಮಾಡ್ತಿರೋದು. ಸೆಕೆಂಡ್ ಪ್ರಾಪರ್ಟಿ ಏನ್ ಹೇಳುತ್ತೆ, if you want the MGF for AX, so MAX of P will be equal to MX of AP. ಅಂದ್ರೆ just P ಇರೋ ಜಾಗದಲ್ಲೆಲ್ಲ AT ಹಾಕಿದ್ರೆ you will get the MGF for the variable Y. So you have some other variable, say Y is equal to AX, and you are interested in obtaining the MGF of Y, then you need not worry about the entire process of obtaining the MGF. What you just do is, in place of your P, replace it by AT. So let me take a particular case. So if I want MGF of say Y is equal to 2x, then MGF of 2x will be e power minus 2t plus e power 2t divided by 2. So I could usually verify this property also by using the problem what we had. So we had x as minus 101, px as half 0 half. So now what I need is, I need MGF of Y, which is 2x. So first we'll define Y is equal to 2x. So whenever we are transforming the variable from x to any combination Y, the probability remains the same. It doesn't change. So whether you talk in terms of x or you talk in terms of Y, it remains the same. So Y is equal to 2x, and that I'll have minus 2, 0 and 2. Now if I want MGF for Y, I will define e power py, because MGF of Y, according to the definition, that will be expectation of e power py, which is nothing but total of e power py into probability of Y for all values of Y. So e power py now will be e power minus 2t, 0, e power 2t. And when you obtain e power py into py, so get e power minus 2t by 2, 0, and e power 2t by 2. So when you add it, you get your m by p is equal to e power minus 2t plus e power 2t divided by 2, which is same as this. So ಇದು ಗೊತ್ತಿರೋದ್ರಿಂದ direct ಆಗಿ put t is equal to 2t. You can generate this, so you can avoid this lengthy process of obtaining the MGF. So that is the meaning of the second property. Now third property, it is for independence. We'll study that in detail when we look into the MGF of bivariate distributions in chapter 4. So let us not worry about property 3 at this time. Chapter 4 ಆದ್ಮೇಲೆ ನಾನು ಒಂದು ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಅದನ್ನ ಹೇಳ್ಕೊಡ್ತೀನಿ. Next, coming to fourth property, it tells if you want to obtain the MGF of m by t, where y is equal to ax plus b, a linear combination of x, then that will be e power bt into MGF of x with 8. ಅಂದ್ರೆ ಏನರ್ಥ, mg of x already ಗೊತ್ತಿದ್ರೆ ನೀವು any y defined as ax plus b ಇದು MGF ಈಸಿಯಾಗಿ ಬರೀಬಹುದು. So let us understand this again for particular cases. So I know MGF of x, which is e power minus t plus e power t divided by 2. Now what I do is I take a linear combination. So let me take y is equal to minus 3x plus 1, and I take y is equal to 2x plus 5. Now, if I want the MGF for this random variable, so I could directly use the MGF from this, and I could say that will be equal to e power bt, which is 1t, into MGF of x with the t replaced by at. So this is the MGF of x. Now in place of t, I have to take at, and a is equal to minus 3 here. So this will be e power at under the minus 3t plus e power minus 3t divided by 2. So you can further simplify this by sending t inside. So you will get minus 2 minus plus 3 plus 1 4. So it is actually e power 4t plus e power minus 2t whole divided by 2. So this will be the MGF of y. Now similarly, if you want the MGF for this y is equal to 2x, so take a is equal to 2, b is equal to 5. So I'll get e power 5t into e power minus 2t plus e power 2t. So the MGF of y for this will be e power 5t into e power minus 2t plus e power 2t divided by 2, which comes to e power 3t plus e power 7t divided by 2. So just by using the MGF of x, we could obtain the MGF easily. So let us verify whether that is true or not. So that is what the proof is. So I have x values minus 101. So I take y as minus 3x plus 1 and I have the probabilities. And now I'll obtain the MGF of y. I need e power t by into probability of y. So when I put x equals minus 1, I'll get plus 3, 4, 1, and minus 2. So p of x is half, 0, half. Now e power yt will be e power 4t, e power 1t, e power minus 2t. That multiplied by the probability will give us this. So when I add, see, I'm getting the same e power 4t plus e power minus 2t divided by 2. So without knowing what is y, what is the probability of y and doing the calculations, we could easily obtain the MGF of y using the property. So that's why we need the properties of MGF. So when you are looking into functions of random variables are also random variables. So in that case, to obtain the MGF, and moreover, MGFs defined are unique for a distribution. So just by knowing the MGF, you could say what the distribution is. For example, in this case, if I say if MGF is mx of t is equal to e power minus t plus e power t divided by 2. What is the distribution? Then the question is distribution is x equals minus 1. You could left out 0, skip 0, minus 1 and plus 1 with probability half and half. So in general, if I say I have the MGF as e power 80 and e power minus 80 divided by 2, then my random variable x is taking two values minus a and plus a with